So I am going to talk about this handout, this PDF that I found online. This comes from Berkeley, UC Berkeley, and I'm sure they're just as great as MIT, and we're just as good too. There's no reason why we can't do their problems. So I'm going to use this for demo problems. And so what I would suggest you do, if you haven't done it already, is print this out. And then you can write on it, kind of read along, and work along with me as I talk about it. I think that would be the most effective way to use it. And I'm not going to go through the whole thing right now because in linkage 1, we're just focusing on 2-point test crosses. And at the end of this, they go to 3-point test crosses. And we'll look at those in linkage 2. So here we have a 2-point test cross. We have some 2-point test cross data. And they show us the whole cross. So let's go with that. We start with the P generation where we have pure breeding. And because these are linked, or even if they might be linked, we don't want to think of the 2 W's together and the 2 Y's together anymore. We want to think of the one chromosome as having a little w and a Y plus, and the other chromosome having little w and Y plus. So that's a plus. Think of there being 2 chromosomes, and we have the W locus and the Y locus, yellow, the yellow body, and the white eye, and they're next to each other. So this parental is homozygous. So to the F1s, she would have to give in her gametes a chromosome with a little W and a Y plus on it. That's all she has to give. And this male, he would have the wild type for white, the mutant for the yellow body, and then he would have the Y chromosome, right? He would be hemizygous. So he's going to give the Y chromosomes to his sons and this X chromosome to his daughters. So the daughters are the dihybrid, and they're going to have a recessive mutant for white and the dominant wild type for yellow on one of their X chromosomes. And on the other chromosome that they got from mom, they're going to have the dominant wild type red-eyed for the white allele and the recessive yellow body. So she is in trans. And so I can figure that out from this information about the crosses. Even if I wasn't given that information, I'd be able to tell from the data. So they've already parsed the data for us. Don't expect that. That doesn't usually happen. But this was probably their demo problem. And so they've got more information here than they would ordinarily get. What we would usually get is we would get the phenotypes. And notice that we're told about the males because the males will be hemizygotes. Sorry, I really can't write complicated things with my finger on my cursor pad because they're hemizygotes. And what this will allow us to see is it will allow us to see the gametes of the dihybrid, right? The males are going to be determined by which alleles mom gave. The dihybrid. The dihybrid is where we can see crossing over. The whole purpose of the dihybrid cross is to be able to tell which gametes represent crossing over and to count them, right? So that we can count the number of recombinants relative to the totals. So we would have these, and so let's see, 6 and 6 is 12, and 4 is 16. I should have worked this out in advance. I could probably just look down the page and find them. So we have 10 and 12, So that's 22, that's 10, 1, and that's 9. So that number is 9026. So we have these two that are recombinants and these two that are parentals. How do I know that? Because these two are about the same amount and they're big, and these two are about the same number and they are smaller. So if there was no linkage, I would expect about equal, right? 1 to 1 to 1 to 1 in this cross for the males. But I don't see that. I see two that are abundant, they must be the parentals, and I see two that are recombinants. They must be the recombinants, right? Two that are small, they must be the recombinants. And then for the parentals, I can look over here and I can see that the parental combinations are little W with big Y, right? Y plus, and big W or y, W plus with little y. So those are the trans combinations. So even if I didn't get this information up here that allows me to know in advance that they're going to be trans, from the data alone, I could figure out that they are trans. So I would calculate I have 129 recombinants. I have 9,026 total number of the offspring or gametes that I've looked at times 100. So if I do that calculation, let me see if they've done this calculation if I go down. Oh, my scribbles don't scroll. They've always scrolled before. Well, crap. Sorry. So oops. I've got my calculator. You can't see it because I'm recording my tab. So 129 divided by 9026 is 0.014. So I have 1.4% recombinants, or I have 1.4 map units. Okay. So that's how I can look at these 2-point test cross problems. I may or may not be given this information about the cross. I will be given these numbers, and I'll be told enough about it so that I know I'm doing the 2-point test cross, so I'll know that if it's independent assortment, I am expecting a 1-to-1 to 1-to-1 ratio. And if I don't see that, if I see this two that are big and two that are small, then I'll know that I have linkage. And the smaller these are relative to this, the more tightly they're linked, the closer together they are. And the less difference there is between the recombinants and the parent and the parentals, the wider apart they'll be, but still close enough together to see the effects of linkage. Okay, in that previous problem, we had an X-linked trait, right? And that's nice because we can have our dihybrid female and we can just cross her and then just look at the males. So the phenotype of the males in that cross for the linkage problem doesn't even really matter. But we are also interested in mapping autosomal crosses. And so here, there's an autosomal problem here that they've given us. And again, they're working it through with all the information. So they're using Drosophila here, and they're using Drosophila symbols. So remember that B, C plus is the same as little b, big C. And so I have the pure breeding female, and then I have my male, who's B plus, that's the same as big B, and little c, right? So they have the, right, they're homozygous, so they'll have the same thing. But the dihybrid has to get one chromosome from one parent. Didn't quite give myself enough room. And one chromosome from the other parent. And so the dihybrid, right, gets a big B from this parent, a little b from the other parent. But now we don't want to write it as big B, little b, big C, little c. We want to keep them together on their chromosomes. And so here we can see that again, the dihybrid has the parentals in trans. The alleles are in trans. So now we're doing the test cross with that dihybrid and a double homozygote recessive. And now we have our 4 combinations, black with straight, brown with curve, black with curve, brown with straight. And they show the genotypes, right? And so these first 2, which I can tell by tracking back the genotypes, or just because these are the big numbers, those are the parentals, right? There's the trans combinations, they're the parentals. So even if I didn't get all of this information, I could tell that the dihybrid was in trans simply because these are the big numbers. They're the parentals. They have the trans combinations. So the parentals are in trans in this cross. I know why in this exercise for this Berkeley class, they keep putting the alleles in trans. It's because everybody comes into this with the idea that they're always in cis. And so as instructors, we're always working to try to help people see that, well, sometimes they're in cis and sometimes they're in trans. So they're kind of hammering the they could be in trans here. And here we would have our recombinants. And our recombinants are significantly less than our parentals. And therefore, we would suspect linkage. And so we can, let me get my calculator out. So I'm just adding these numbers, 2934 plus 2768 plus 871 plus 846. And that's 7419. I need to practice with my writing with the little pen on the cursor. Or invest in one of those fancy tablets that uses the stylus. Okay, and now I need my number of recombinants. I think I can do that math in my head. Now let me get the calculator back out here. So 1717 divided by 7419 times 100 is 23.1%. Equals 23.1. 23, come on, show up. There we go. 23.1. And it would depend on what we were asked. If we were asked, what's the map distance? We would report as 23.1 map units. And if we were asked, what's the percent recombination, we'd say 23.1%. But it is the same number. Now, this goes on and talks about chi-square test. And we will talk about that elsewhere. So here we see 2 examples of the 2-point test cross, the very most basic type of cross. So sometimes we're given this crossing information and sometimes we're not. Sometimes we're just given this much. And then we have to figure it out. We would have to know which is dominant and which is recessive, right? We would have to know that black is the mutant and curved is the mutant. We would have to know that much. And then just with these data alone, we could figure out that it's linked, that our parentals are in trans, and then we could calculate our map distance or percent crossing over.